All right, so this is basically a cellular automata, Conway's game of life animation, with different rules. So we start with random array of cells, and then we assign a true or false state for either of them. So imagine, let's actually, we could start with all of them being false. Okay, so we will start with basically an empty canvas. So, and then I'm going to do it this way, and we could also add a stroke here. So let's add stroke to be 0. So I'm just going to visualize basically a white grid, something like this. Let's also make the cell size to be large. So I'm going to make this 20. So these are all the cells. Okay, so this is 20 pixel per cell, and I'm initializing all of them to be false. So that means if they're false, they have a yellowish color. If they are true, then they have a bluish color. We can also change these colors here. C1, C2, I think, is used to interpolate some of these values. So if they're false, we get this value. So I can also make them white. So I can just make it here, fill 255. You can see they're all white. Now, what I want to do is actually show you kind of how the grid works, okay? So if you remember here, we have a mouse pressed function. The mouse pressed function actually gets triggered with, let's actually look at what it does. Mouse pressed T5. So this is a built-in function. And what it does is click within the image to change the value. So basically, it could be triggered when mouse is pressed. Okay, so imagine this to be a condition. So this gets called when you press the mouse on the canvas, all right? Or when you press it anywhere on canvas. If you press your mouse, then we are inside this function, no matter what. The other interesting thing is inside of this, you can also use mouse X and mouse Y. Now, these two parameters are traced all the time. So for instance, inside draw, I can just print my mouse X and then print my mouse Y. We can also write them this way. So my X is plus string mouse X. And then we could also do my Y is, and this is mouse Y. So when I press play, now wherever I move with my cursor, you can see that we are plotting some integer values, right? So that's basically the pixel location of my mouse cursor. So on the left top, it will be close to 0, right? Remember that this is 0, 0. On the right bottom, it will be basically canvas size. So whatever the width and height is. Now we can actually convert this using mouse pressed for the cell, for the cell in our grid. So basically, inside mouse press, we can use mouse X and mouse Y. And this already gives me the neighbors, like we already wrote this function, but we are counting or calculating the location of the mouse. So what I can technically do is get or access the list and define two variables here. Let's call it let X. X would be this, right? What do I do? I'm basically dividing the location, the pixel location of the mouse with the cell size. So if I'm at 1200, then I divide by 20, and that would be that'll be what, 60th cell horizontally, right? And we can also do it for Y coordinate. And we keep doing mouse Y divided by CS. Okay. And then I can do this. Basically, I can override not I can get the current state and I can turn it to be the opposite of it. So this this exclamation mark in computing language is basically turning it into an opposite. So if this is false, it will become true. If it's true, it will become false. I can also write it this way. I can make it true, but that will only turn the cell to be true. And if we want to turn a true cell to be false, then we have to write it in the not configuration. So I have to write not cells XY. Okay. So when I run this, now if I click anywhere, let's see, it's not converting it. Flute. Oh, this has to be floor. I had a typo. Now I click here. You can see I'm actually turning those cell states manually, right? So what do I do? What I do is I find the XY location of that cell, and then I convert it to the array location of the cell, and then I override the state of that cell. Okay. So now if I click on the same cell, it will turn to be a dead cell, right? It's because I'm changing its state to be either true or false. So we can actually keep debugging a few more things. For instance, what I did was I calculated the neighbors here. We have a get neighbors function. Where is it? So here we supply an XY location, and then we basically get the neighbor counts. Now I can have another version of this. Like I can just copy that function and write it something else. So we not only change the current, maybe we don't want to change the current state of these cells, but we want to change their neighbor's state. So what I can do is, who can actually write it? So let's make this into a quiz. Shall we do it? Let's do it a bit more interactive today. So let's say that what I want to do is I press play. So I want you to write a function here, okay, that takes my mouse X and mouse Y. All right. And then I want it to get the state of the cell where I'm clicking at, but I want it to basically turn the state of its neighbors, only if its neighbors, to the opposite. So I just use this XY coordinate for the cell, but I want to turn the state of its neighboring cells. So let's make that into a quiz. Okay, so you don't, if I click here, I'll describe it again. If I click here, I don't change the state of the cell. I just change the state of its neighboring cells. Okay, so I want you to define it as a function. So it will be written something like this. Function turn neighbors, or let's call it switch neighbors. Switch neighbors function, and it's going to take X and Y. Okay, so I'm going to leave this on the screen, and I want everybody to write this. Try to write this. Okay, you have everything you need visible on the canvas. So I'm going to wait a bit, and I want you to try to write this function. Did everybody understand what we are trying to do?
Yes.
Okay, cool. Let's try to do this, okay? I'm going to give you 15 minutes. If you have any questions, you can write in the chat as well. Resume recording. So one way to do this is to, for instance, get the left. This would be its left, right? Equals not cells XY. This would be the left cell. Let's write the right cell. That will be X plus 1. Then what are top and bottom? Top will be Y minus 1. This would be the bottom cell, right? So this is it. So we don't change the state. We just use the current cell state, but change its neighbors. So the ones on the left, these are its neighbors, left, right, top, and bottom. So I'm just doing, what was this called? Moore neighborhood. So it's, so when I click here, only its 4 neighbors change state, right? But the problem is, when I click on the same cell, they don't change the state. The reason is because we are not overriding the current cell state. So for instance, if I enable this too, then it will be, it should be a plus sign, but let's see. We should do this at the end because we first use negative here too. So it will be a plus. And if I click on the same location, then it won't. So what will happen if they intersect? Interesting. Oh, they're also calculating some sort of hue, probably. You can see that I'm also using the neighboring count to calculate kind of a hue of the color. So the ones with the least amount of neighbors, they're the darkest, and the more neighbors they get lighter actually. Okay, so I'm basically changing cell states this way. Okay, but this is kind of a longer way of doing it actually. We can turn this into a function. So we don't have to do it here. Let me actually comment this out. But what I can do is use something like this, get neighbors, but rather than using that, we're going to use switch neighbors. So all I have to do is copy these double for loops and basically access the neighboring cell states and turn them to be not the current cell state. Okay. So technically speaking, we can also use this function. What would this do? This would, if you remember, this would wrap the values around. So for instance, if I'm at the left border of the canvas, we want to get, we don't have a cell on the left side of it, but we want to get the cell on the other end of the canvas, right? So this is basically enables us to do some wrapping. So I can get this state to be not cell state. And at the end of it, I can just turn the cell state to be this, right? This was basically the solution. So let me see if I'm missing anything here. So this is correct. This needs to be like this. I guess this would work. Let's try. And I have to also call this function now. So switch neighbors X and Y. So when I write and I click here, interesting. So we didn't get the other side. Why not? Let's see, why didn't we get the other side? It only creates these. So X equals X minus 1, I less than or equal to X plus 1. So that seems to be correct, but let's see. Not cells XY. Why didn't it work? Well, I didn't get the right side. Let's see. We have to debug this. This basically is kind of the cells around us. If I equals X, J equals X, Y, we continue. Oh, I see what's going on. Who can tell me what happens here inside this for loop and why don't we get these cells? This is actually an interesting programming question, but who can tell me what's happening and why aren't we getting these cells to turn their states? Nobody? So you can see that here I'm skipping the current state of the cell, right? So when I equals X and J equals Y, we want to continue. The reason is because when we are tracing these cells, so I start from the left top, right? So when x is minus x minus 1 and j minus 1, that this is the cell. Then what we do is we increment y, so we go down. So I visit these cells. Then I switch to this for loop on 75. So x becomes basically x. So we turn the switch on this cell, but then I move the current state of the cell, this location. So basically x equals y. And what happens is I turn it to be the opposite of it. So this becomes basically false, or it becomes true. But then when this becomes true, the remaining for loop cells, they become false, right? So these 4 cells now, they become false because we turned the switch on this one to be false. So what we have to do is we have to implement this routine here too. So we skip the current cell state. Now, if I do it this way, now you can see we're actually turning the switches on all the neighboring cells. Now, there's an advantage to doing this way. It's because basically we can also change the offset value, right? So if I type in let offset equals 3, now I can use this to be kind of how many neighboring cells I want to visit and how many neighboring cell states I want to change. So when it's 3, now when I click somewhere, I basically go all the way out. And let's see why it doesn't revisit these cells. Y plus 1, that's basically correct actually, but let's see. This is only changing here and it's not changing the states here. Why is that? So I want it to basically also make these cells that I'm tracing to be blue, let's say. How do I do that? What about when offset is 1? That's basically, we didn't do this to be offset. Let's make it like this. Okay, so that's correct. When offset is 2. Okay, so we get an offset, but we don't get these to be different. Why is that so? So it's I starts from -2, or whatever the value is, and then goes to +2. Y does the same. When I equals x and j equals y, we continue. Then we do a num here. So this is kind of the mod, not cells. Okay. Interesting. So we don't do this here. That is interesting. So when we do this here, then it doesn't seem to work. Or there's a bug probably. Right, so now I'm basically having a mark where the hatch is getting kind of thicker and thicker. So I can make 1 offset, I can make it 5 offsets. Okay, but why is it? Let's see. Why is it not tracing all the cells inside? This is correct as well. What am I missing? That seems to be correct. I mean, you can also do prints. print I, for instance, and print J, and let the offset to be 2. These are all the values. So 0, 9, 8, 9, 10. Why does it start with 0? Starts with 0. Those prints are X and Y values. Let's print these. strx, stry. So 12th and 12th cell we are printing. There's a print 0 coming in somewhere. So I probably have left some print somewhere. So this is printing 0. Let's see where that print is. Oh, this one. This line, we can just comment it out. So when I click here, so I'm looking for the X, the cell horizontally to be at the 11th position and vertically in the 13th position. So we are starting in this for loop. Offset value is 2. So X becomes 9. So X goes from 9 to 13. Y is going to go from 11 to 15, right? So 9, 11, 9, 12, 9, 13, 9, 14, 9, 15. So that's like the left row. Then it switches to 10, 10, 11, 10, 12, 10, 13, 10, 14, 10, 15. So then 11, 12, 11, 13, 11, 14, 11, 15. Then we do 12, 11, 12, 12, 12, 13. That seems to be correct, actually. Like the for loop is revisiting all these cells. Now, when I make it 3, why is it changing these states? Or maybe it has to do with the neighbor function. I'm wondering if it's just a neighbor count, because we are, don't forget, we are still visualizing based on the amount of neighbors we have, right? So I can just visualize them to be a single color. So for instance, fill C1, let's try to visualize it. Yeah, I mean, I think our code was working fine. It's just because the cell is neighbored with a lot of active cells, it's getting to a white hue, right? So the lerp color function, the maximum amount of neighbors we have is 8. So if it's 8, then it becomes kind of a whitish tone. So this code was actually working fine. So now you can see I'm actually putting kind of a paint marker, almost kind of like an 8x8 grid. So we can make this as wide as we want. So if I make it 5, I'm going to delete these. Now we will draw a 5x5 grid around where we click, right? So that for loop is basically overriding the cell states within that 5x5 grid margin. Okay. So let's do something interesting with this. I mean, I want to show you first how we can access the cell states and the cellular automata list. What I want to do now is, let's say we make a symmetrical composition and let it run for a while. And then maybe we populate it, we increase the amount and see how we can actually do this. So do you have any questions about how I did switch neighbors? Let me ask. So now we can actually switch to neighbors based on an offset value. So I can know how far the cell is from the current grid cell. All right, next thing I want to do is I want to start with a seed, or let's say a row of seeds. So imagine we have a row of seeds here. These are the cells, and they could be in any type of configuration. And I want to let this kind of grow around. So I want it to shoot in like all kinds of directions. And the way I want to do it is by, let's say that we assign kind of a seed value, seed configuration. So what if that seed configuration is something like this, right? So we start with an offset value of 1. So this would be how we start, okay? And I want to see how actually it propagates. So I want to enable the next generation so we can update the calculation of Conway's game of life. So wherever I click, that should basically start moving around, right? So because next gen is now available. And if I click somewhere else, that would also start growing. So now this is kind of interactive, you know? Now it's hardly patterned actually. And it's interesting because it's kind of growing asymmetrically too. So which makes me wonder whether we can actually have a different type of seed configuration. For instance, if I make this 2, let's see how it kind of animates. This also grows asymmetrically, but I want to have a symmetrical initial configuration. So what if we don't do X and Y to be the same? So I do let offset X and let offset Y. So what if this is kind of a vertical thing? So this would be here, and this would be here. So now we will have a rectangle. It still grows asymmetrically. I mean, maybe it's the rules, the cellular automata rules that we have. Yeah, it always grows asymmetrically. Maybe we change some of this stuff. So if we do, for instance, this to be 3 and this to be 2, that will be the original cellular automata rule. Wow, okay. It's shot. Oh, interesting. Wow, it changed a lot of cell states. That was interesting bug. So if alive is less than 2 or greater than 3, but if it's equals to 2. If cell is alive and less than 2, this is kind of the neighbor count, okay? How about this? We make this to be 4. What will happen? Yeah, you get kind of, wow, it still shoots up. Interesting. Yeah, you kind of get different types of behavior. There's kind of unlimited possibilities here, which is kind of fascinating. We could also make it in a way that we don't use the Conway's game of life rules here. Like I can have another function here called next gen 2, right? This could be a custom function. So we can only go by, let's say, like when we do to get neighbors, we don't look to 8 cells, but we look maybe to 4 cells. We can also do that, right? So here, for instance, get neighbor algorithm. What I want to do is, let's say I want to just look at these cells, not the 8 neighboring cells. I want to skip the ones where I put the dot. So that basically means, I mean, we can just like manually write this probably. So I can have another function gets more neighborhoods. Was it more neighborhood? Let me check. Neighborhood cellular automata. Yeah, the more neighborhood is the 8 count actually. There's also another one. Von Neumann neighborhood. Yeah, von Neumann neighborhood is the 4-1. The other one is in 8. So we are doing von Neumann, so we can call this VN neighbors. So this will be more neighborhood. This is more neighbors. So 8 count. This is 1 Neumann neighbors. So similar way, we can have a different neighbor check, right? So this is 1 Neumann neighbors. This is actually 4 count. And I can just copy these, right? So it's basically we're just looking at the count of left, right, top, and bottom. So technically speaking, I can start with the count value, let count equals 0. And if these cells are true, then we want to increment this. So we can write it like this. If cells x minus 1, y, then count plus plus, right? And 4 times, and we want these to be here. This to be here, and this to be here. All right, so this is left, this is right, this is top, and this is bottom. So that will give me the total number of counts and return count. So now I can use this instead. Cool. Okay, so we could do left alive equals get 1 Neumann neighbors ij. Right? Now we only get so we won't use these rules because we won't have more than 4, to be honest. So we can just have a threshold. So let's say if cell is alive, or we can write a custom rule here even. What shall we write? So if cell is alive, and we can also call if alive ratio, right? So if alive is less than 2, we can give it another type of state. Else we give it a different type of state. So I'm just throwing out some random values, something like this, less than or equal to. So we're going to check for 4 neighbors. If the current cell is alive, this is true. I'm totally making this random, but let's see what we're going to get. So this could only be a live neighbor count can be between 0 and 4 now, because we're only looking for 4 neighbors. And if our current cell state is alive, then if our neighbor count is equal to 2 or less, then we're going to make the current cell to be a dead cell. Else we're going to keep it to be true. So that means we have a lot of alive neighbors. So we can keep it to be true. Else, if the current cell is dead, if it has less than 2 neighbors, it's going to become true. Else it's going to be false. So I switched these two, and let's see how it's going to behave. I have no idea. So let's see. I'm clicking here, but nothing is happening. So let's see if I'm missing something. Switch neighbors is doing what we expect it to do. Let me actually turn this off. Okay, so this is working. So when I enable next gen, let me see if oh, I'm getting an error. Can I read properties of undefined 0? Line 62. What is happening at line 62? Oh, all right. What is the problem? Well, we are looking for left, but when x is 0, we don't have a left, right? So we need to implement this as well. So we need to modulate it. So I need to do this. I need to get this value. And then add plus num, mod num to it. Num was basically the number of cells. Yeah, that's basically what we have to do. And this has to be x plus 1. This has to be for y minus 1. This has to be for y plus 1. Yeah, I think this would work now. Oh, wow. They all turned blue. Okay, so the rule basically turned them to be blue because, well, when you have less than 2 neighbors, it maybe becomes true automatically. So maybe we also do it this way. So less than 3. Oh, wow, it dies a lot fast. So it doesn't stay up. Let's make this 1 if live count is less than 1. Well, it stays like a block. Well, that's not good. Maybe we make this 2 again. Well, these more neighbors do not propagate here. How can we solve this? Maybe we implement a structure that can generate symmetrical structures, but yeah, this doesn't work. Any ideas? Maybe we switch to this one? Or maybe I can also implement this. I don't know. Let's try. Let's try this old rule. Well, it doesn't propagate though. Yeah. Yeah, it shoots up. I don't know why it shoots up. It's kind of growing exponentially even. We're getting kind of a nice pattern. Like here we get a checkerboard, here we have some like larger cells. But yeah, what I wanted to do was like make this to grow symmetrically, right? Kind of like propagate. So maybe we can actually achieve it by increasing these values to be kind of huge values. So what if we do it this way? So if the current cell is alive, underpopulation, overpopulation, that's fine. So let's make this kind of a lower threshold. I mean, we are not checking for 4 anyway, so we can just do it equals 4. And else we just turn it to be true. If this is alive and the neighboring counts, if this is dead and neighbor counts is 2, then we also turn it to be alive, or we can make this just like greater than 2. Greater than or equal to. I think this will propagate a lot more. Oh, it's just flickering inside. Interesting. Now they're interacting. Well, it's like almost like a cell animation, no? Wow. Okay, this is interesting. So when we have a border, and now it's propagating, and it just stops. So when it has an edge, it just stops. Interesting. Kind of like fills up a rectangular grid and then animates it. Very interesting, no? I mean, there are tons of rules we can experiment. And this is kind of flickering behavior almost. Maybe it's because of this too. What if I just make this like that? This is interesting. It just stays. Why? So for this cell, we only have 1 alive neighbor. So this doesn't turn on probably. That's why. Okay, so this has to be if it's a neighboring cell. So if I do basically greater than or equal to 1, then I think this would work. So now it will probably move around. Well, it just shoots up though. It's so weird. This looks like so buggy. It's interesting. So probably this is growing exponentially all of a sudden because there's so many cells that are alive. How about this? Then it doesn't do it. So let me switch to the old neighborhood. Less than 2, greater than 4, and greater than 1. This would also shoot up probably. Yeah, it's so weird. Just like switches between 2 states. Let's do greater than 2. Yeah, now it's propagating. So when we make it 1, it just it seems like it becomes, yeah, this is like just flickers. It's also changing the movement, but yeah, but this rule is kind of the problem because it kind of creates this, when we have this flickering behavior, it's because of values of 2, right? Because wow, now it's rippled. This is so cool. Wow. Yeah, now we have like almost like a movement animation towards the right, right? I mean, let's make this 3. Let's see what happens. All right, it's staying kind of small. Let's make it double, triple. Interesting. It just turned into almost like a cell animation like this and just stays like that. Very interesting. So let's do y to be 5, x to be 2, and see what we get. Yeah, this doesn't give much structure either based on these rules. How about 1? I'm kind of adding patches of like cell states to see if they simulate. We could also do it in another way. For instance, we could also have a list that keeps track of visited cells. For instance, we can make the structure grow and don't animate a cell that has been visited, right? That could also be kind of a final implementation of this code. Basically, the reason why we see flickering behavior is because a cell is constantly updated based on its neighboring count and neighboring states and based on these rules. So it's kind of hard to find a stable differentiation. Maybe we could also do, for instance, we did one-dimensional cellular automata bit where we plotted the kind of cells, but we can also probably do it. Well, we cannot do it one-dimensionally, don't we? I mean, we cannot do it two-dimensionally. We need kind of these neighborhoods like Moore or von Neumann neighborhoods. So that becomes an issue. But if we keep track of the visited cells, then that means basically that those cell states do not get updated. And that would be kind of an easier way to do it. For instance, remember that we have cells, new cells, right? So we update the cells based on the next configuration of cells. So we have to compute this list and we then override it. What if we have a third list called visited, or call it V cells? These are visited cells. And then if we visit a certain grid point, then we don't update it, right? We just store it to be true. And that will also create a mapping. So we can actually start it here, kind of a third list, and then start it to be all false. And let array num. Okay, and this is V cells I and V cells ij. Now, what we do here is what's cool. So when we do switch neighbors, we want to not only switch this state, but we also want to update the visited cells because we are technically visiting those cells. We don't want their state to change, right? So we want these to stay true. Yeah, that's basically correct. And then when we are calculating next generation, we get the alive count, and then we get the cells. But we can also do it this way. If, for instance, if the I and J belongs inside the visited, so if V cells ij, so if this is true, if this switch true, then technically we just continue. Do we continue or do we keep the state as is? Or I think we just keep it the way it is. So if it's visited, we just want it to be whatever it is. Yeah. So we want the next generation to be the old generation. But if it's not, if basically else, then we basically apply the neighborhood rules. So we calculate neighborhoods, and then we basically get these rules implemented. Right. And then we basically, this is not in the visited cell. So if it's alive, we just calculate this, calculate that, blah, blah, blah. But if we are making it to be true, then that means basically it's becoming visited, right? So we are constantly increasing the neighbors. I think that's what we have to do. So yeah, we have to also update the V cells. Let me actually test how this works first. It's giving me an error already. V cells is not a function. Oh yeah, this has to be like this. If V cells. Yeah, so this stays kind of a rigid block. Let's we update. Okay. Why didn't it work? Kind of making it more complex, I feel like. What if we do kind of this to be 1? Or even 0. Let's make it into a single row. Just stays. Yeah, it's not. Well, maybe we don't use cells. I don't know. Well, maybe we do it for next generation. So if its cell is alive, and we mark it as visited maybe, then we want to skip it in the next generation. How do we do this? Let me actually delete this part. Yeah, I don't want it to ripple. I want it to, like when it updates a cell state, I want the cell state to stay just the way it is. So that basically means when we visit a cell, we don't want to revisit it again. So we want to skip that list. So that means like if I'm in a visited cell state, then I basically have to continue. But the problem here would be, well, actually, we are looking at its counts, neighboring counts as well. So maybe we just do this. So if V cells ij, we just continue. Let's see what happens. So if it's in a visited cell, remember we have 3 lists now. Yeah, these cell states do not, oh, these do though. These do update. So it's still flickering. Well, it's probably we are not overriding this, that's why. So it's becoming true or false. When it's becoming true, maybe we just make this to be true as well. So how do we do that? So if it becomes true, this becomes true too. And this becomes true. Okay, much more like this, but it will just keep growing outward. And stop, kind of a bloat. Well, these are visited. That's why they don't update, right? They stay the way they are. Let's make this 2 by 2. And well, maybe we change these rules. Yeah, it just keeps growing outward. And then shoots kind of really fast. I guess this has to be really, really large. And well, I don't know. Let me see if you have any questions at the moment. Like what I was trying to do is basically get this to kind of create kind of a patterned behavior outward. But the issue is well, we are just overriding some states. But I don't have a way of keeping track of where we visit, right? So we are trying to plot kind of a pattern, and we want it to stabilize and stop updating, basically. So we don't want it to ripple, so to speak. And that involves some sort of rule check, basically. And if this pattern doesn't establish itself, then we need a way of stopping the flickering, right? Because it might change an older cell state as well. So I tried to implement this visited cell list, which basically means if we are tracing over some area, some region, we also want to mark those cells to be visited so that we don't change their states, right? Because if I'm updating this list, then I'm technically keeping track of the cells that I visit. But I'm only doing it for the true states, but we should also be able to do it for all kinds of cells. I think that's why we don't get any pattern. It just makes it into a bloat, like a blotted shape. Let me actually get to the older version. We're actually not going to use visited cells. Also, this is not required. Let me see. We are not using it anywhere else. Yeah, it's kind of interesting because it does this sort of gridded behavior, and the problem for me is it doesn't move outward, right? It just, the animation stays inside. I think that's kind of the issue that I have with this. It kind of moves very nicely. It's because of these rules. If I increase this to be 2, I think it just shoots really fast. Well, it moves away, kind of ripples. Now we get some sort of movement. This could also, well, then it becomes flickering, right? Because of the, like, it meets a condition here that satisfies this rule set, and it just updates all of cells one after the other because of this neighborhood. What if we do 1 Neumann again? Well, this doesn't move because it has only 1 cell that is alive. If it's greater than or equal to 1, then I think this doesn't work. Yeah, it just shoots immensely fast. Maybe we can look for some neighborhood rules from 1 Neumann. Yeah, this has to be 3 or 2. Just like this, when this is 2, it just updates all of cells really fast. This is also kind of creating a ripple, but yeah, now we get flickers. It's now moving down. I think it's interesting. I mean, it's kind of a animated field almost, right? And you get to see the kind of behavior. So you get kind of a dotted pattern, striping pattern. Let's actually make this a bit more colored resolution. And I'm going to decrease the cell size and also enable hues for the colors that we used to have. So let's see. Nice. All right, let's see what's going to happen. It's at some point it's going to shoot up probably. I'm going to probably turn off the stroke, but you can see the cell sizes. Now this has a lot more pattern, right? You can see stripes, you can see dots. It's a bit, it's kind of visually striking, but yeah, now we get the flicker, but it's going, that area is going to be invaded. All right, let's do one more thing. I'm actually going to do this faster. Increase the frame rate to be 12. Decrease the cell size to be 5. And one more thing, I'm going to turn off stroke. So I'm going to make it no stroke, which we already do here. So let's see what's going to happen. You can also start from multiple seats, right? I can click on different locations. I'm not too fond of the flicker when it's animating, but it's because of the rules we implemented. But what's nice is that you get kind of structure, right? So these stripes forming, it's kind of almost like a waving animation. So they look like, if you look at the right, they look like this is kind of moving towards the right. These are moving towards the bottom. So there's some sort of movement in the field almost. Yeah, this kind of stabilized, interesting. This part stabilized. Let's actually try one more thing, which is I'm going to decrease the cell size and increase the frame rate. Let's see. So the cells are really, really small now. So we are updating almost every pixel. All right, I'm going to stop here today. Want to do another animation piece. Let me see if you have any questions. I guess this, you can see here, like this is the reason why this is shooting is because remember that we have for loops, right? So if I'm looking for the cell state, I'm always tracing, like if I'm changing this current cell state, I'm also affecting how this propagates diagonally, right? Because if this is turned on, then it affects the subsequent for loop calls, because like these cells are being checked as well. And if this cell gets checked, then this kind of creates this ripple all the way downward. So that kind of like shoots downward. I guess it has to do with the neighbors because it meets some sort of configuration. It then updates it. But yeah, this is pretty interesting. I think like it's kind of animating still. It's also taking all of time to update because of the amount of cells it needs to traverse. We can also probably make this smaller, but it's almost same as increasing the cell size and keeping this resolution, right? So if I basically make it, wait, stop this. If I make this to be 20, yeah, it's kind of epileptic almost. Yeah, this is like too fast. Let's do 5. Yeah, that flicker. Yeah, you can almost see there's some sort of pattern, like there's some sort of movement in the grid, right? It's like ripples moving in kind of an established direction. Maybe we can make the colors to be less contrasted. I guess that kind of creates the effect a bit, like white and black, like there's too much contrast happening. And then you can see some sort of structures emerging as well, like these lines are quite visible. There's a lot of complex behavior we can actually simulate with this. So this was C1, C2. I guess we don't have to make this white. We can just make this was probably, we can just make it, let's say 100. This is 120. And this is going to black. Let's make it go to gray and see what we get. Yeah, a bit more, like I desaturated it a bit so that it doesn't have like the flicker doesn't bother us as much. But we can still see, I mean, this gray is making this too. Maybe this could be, this was going to white actually. I made the blue a bit darker. Maybe 20 or 10. All right, do you have any questions for me? We're going to basically wait for the lecture a bit until 12, but we could give a break. Do you have any questions about this animation? Right, it looks like waves actually, waves in the ocean. And you almost see like kind of a riverbed from the top view. And there's some sort of movement based on, I mean, this was quite by luck actually, like I just played around with the Serial Automata rules, the neighborhoods, implemented some different rule sets and see what kind of behavior we get. And this is all experimentation basically. I mean, there are endless possibilities here. You can also implement different types of rule sets. But I mean, you can actually work with these gridded cells. I think for animation, they're quite easy to implement. And they're also easy to debug, I think, because you know you can actually retrieve the information of each cell. You can use your mouse to interact with the data. And you can also play around with color and other types of behavior. All right, I'm gonna stay here. And let me know if you have any questions. Otherwise, I'll meet you again towards 12, where we have the lecture. Any questions?